Thanks everyone for coming. So my talk is a little bit about the story that we saw at Google and how we arrived to Kubernetes and the pieces that are part of Kubernetes. So the message that we always use to start talks is about how at Google we have been developing something that is for Gmail and YouTube and Google Search, but all these small pieces that we have been developing internally are the parts that are part of Google Cloud Platform and are the pieces that people can use these days. Because we believe that the next application that is going to be based on Google technology is not going to be done by Google, it's going to be done by someone else. So how many of you have actually seen this slide already, or something similar? Okay, so not that many. So these are the names of some of the tools that we use internally at Google, and these are the names of applications that are actually deployed that we use to be able to deploy. So when we're talking about Dremel or we're talking about Bigtable, we're talking about actual software. But this is also the name of papers, of white papers that we have published. And based on these white papers that we published to discuss with the research world, based on that, we have open source implementations. So we can talk about Hadoop, which is based on MapReduce, a paper from Google from 2004, or MongoDB and Cassandra, kickstarted by a paper about Bigtable in 2005-2006. And what you can see in the last 3 years is that we are opening the exact same tools that we use internally. We're giving it an external name, an invoice interface, and external documentation. And we're opening that to the public. So something that internally at Google we know as Colossus, which is our file management system, is something that is open to the world as Google Cloud Storage, or Dremel as BigQuery, etc., etc. And today I wanted to talk to you about two specific projects, Borg and Kubernetes. So containers, and I'm not going to ask how many of you know about containers, but how many of you are actually using containers either in test or production? Okay, that's great. I'm in the right place. That's cool. So yeah, we all know about, I'm going to skip all the introduction about containers, and I'm going to just stay on this one. Like, we are developing a system where virtualized software is better, where we can deploy more optimized environments, where our virtualized environment does not include a second operating system because we don't need a guest operating system. This is more lightweight, this is better performance. But then, when you're deploying this kind of stuff, which kind of tools are we using to deploy? At Google, we have been using containers for more than 10 years. And these are not Docker containers, these are Borg containers, a different technology, internal to Google. And what happens is that after 10 years, today at Google, we are deploying 2 billion containers per week. And if you do the math, we don't have enough people to do that. We need better tools, tools that allow us to deploy and think about clusters, not about individual nodes, and think about applications instead of thinking about individual containers. And this is how Kubernetes started. These are some of the contributions to the open source world related to containerization. From 2004, where we had limited isolation with chroot, etc., to cgroups, which is part of Borg that was contributed by Google to the Linux kernel in 2006, and which is the foundation of anything that came afterwards, like anything based on containers, say Rocket containers, Docker containers, all of that is based on cgroups in the end. And cgroups is part of Borg that was contributed back then. And then let me contain that for you, which is actually a thing. Let me contain that for you. It's an open source project available on GitHub that is parts of Borg that we wanted to contribute to the world as an open source project. At some point, let me contain that for you was not useful anymore, and we discontinued the product, and we contributed the core ideas of let me contain that for you into Docker, which is part of Docker, actually, these days. And then there is Kubernetes. And Kubernetes is a special case. Kubernetes is the response to a question that we had at Google. OK, what if we take the last 10 years of improvements to Borg? 10 years where we have been learning what works and what doesn't, and we have been incrementally improving Borg. And instead of talking about a software that has been evolving for 10 years, let's develop something from scratch today. Let's make it open source, and let's open this to the public. And this is Kubernetes. Kubernetes is a container orchestrator. That means that it's awesome to think about Docker containers, but how do you connect containers between themselves, and how do you manage the load balancing? And this is something that we're going to see today. Kubernetes is built on containers, not necessarily Docker containers, so I'm going to focus a little bit on Docker, but Docker and Rocket both are considered inside of Kubernetes, and CoreOS is a huge contributor of Kubernetes. Kubernetes handles both container and node failure, meaning that it's not only the container that can fail, but also the node, the physical machine that is hosting the container. And it's 100% open source, and that's something great. I mean, this slide is already outdated. Top 0.01% of all GitHub projects, that one is missing 10 right now. Kubernetes is right now the top 0.001% of all GitHub projects. It's the number 2 Go project right now, today. The number of external projects is 1,000, a little bit more than 1,000 external projects. External contributors, let's say that we have 5,000 contributors, not contributing on GitHub, but on the Slack channel for Kubernetes. It's one of the projects that is growing faster these days. These are all committers to the Kubernetes project, including, I don't know, CoreOS, Red Hat, IBM, a little bit of everything. And I wanted to introduce a little bit some of the components inside of Kubernetes and the ideas behind that. I mean, like, why did we arrive to this? So when we are deploying containers, we discovered that sometimes associated to a container, we need more containers, and we need to guarantee that all of them deploy at the same time. And this is what a pod is. At Kubernetes, we don't talk about individual containers, we always talk about pods. And when talking about pod, you talk about several containers that are required for everything to work normally. So containers in a pod, they share the same TCP/IP stack, meaning that they share, they can communicate via TCP/IP, and they can communicate via sockets on localhost. Pods are considered to be ephemeral, meaning that it's totally normal if your Kubernetes cluster is rebooting your pod while you're not looking at it. It's totally normal. So you can see every now and then that your pods have been rebooted somewhere, somehow. Think about it this way. When you are deploying 2 different containers, and you want to deploy them inside of a cluster, and you're considering, OK, should they be in the same pod or not? Example, I have an Apache, and I have another container, separate container, that is managing the monitoring and logging of my application. That's a perfect example for a pod. They can communicate using localhost, which is extremely performant, and they are both required. You cannot deploy this Apache without your monitoring container. So that's perfect. But if you think about your Apache and your Redis server, they probably are better in separate pods, because that way they can scale independently. You can have 3 copies of this, but 2 copies of this. And Redis, strictly speaking, is not required to be able to deploy Apache. So when deploying on your pods, you have to make your own personal decisions, but use this as a grain of salt. Typically, 1 container, 1 pod, that's the usual case, but you can find exceptions out there. This is an example in terms of code. With Kubernetes, everything that you are deploying is a file. It can be a YAML or a JSON file. These are files that are going to be sent as is to the master, and then your master server is going to take this file and then start talking to all your nodes, orchestrating your services. All our examples today are going to be based on YAML. And what you can see here, the first thing that you specify in your file is which type of resource we're defining, which is a pod, and which image. And images, when they have this look, we're talking about the standard Docker images that go to Docker repository, the standard Docker repository. But we could be talking about a slightly different URL form, like this. Images with that name, they are stored on your own Google Cloud registry, on your own Google Container registry, which is a free service that you have with your Google Cloud project. So when we are talking about containers, for those that are not familiar with that, we could be talking about Docker Hub. There are many different repositories for containers, but these are 2 of the most common ones if you are working with Google Cloud. Docker Hub would be the public containers, and these public images, they are either official, or it's a little bit like GitHub, that any user can have any number of images. And then you have Google Container Registry, which is your own private registry where you can upload the stuff. This is a free service. You only pay for the storage space that you take. And both are can be integrated with Jenkins, Travis CI, anything that you're using for your own continuous integration environment. So we have pods, and each pod can have multiple containers inside. And if they are deployed, either all the containers are deployed or none of them are. And then we have nodes. And nodes are the physical machines where these pods live. They can be physical machines if you're deploying on your own data center. Think about it. Remember that Kubernetes is an open source tool that you can be deploying on Google Cloud, on Amazon Web Services, on your own data center, Azure. You have Ansible playbooks for almost anything that you can think about. So this node could be a physical machine, or if you're deploying on Google Cloud Platform, it can be a virtual machine instance. So we have pods, which are our containers. We have nodes, which are the physical machines for these containers. And then we have services. And services are an IP address and a URL that are going to act as a load balancer for all our pods. So this is going to be a fixed IP address with a fixed port number, and services are expected to be a stable entity. There are two different ways of declaring a service. One can be a cluster IP, and the other is load balancer. So load balancer is going to be an entity provided by your cloud platform provider. On Google Cloud, that's a Google Cloud Platform load balancer, which is based in our maglabs, our internal load balancer technology. So you could be using type load balancer, which is provided by your cloud provider. If you're going with Amazon, it's going to be an Amazon load balancer. And if you're using cluster IP is going to be a software-defined entity. What Kubernetes is going to do, it's going to configure an HA proxy for you, and it's going to automatically configure that. So you don't have to see it, but it's going to be there, and it's going to be accepting traffic. And then this service here is going to be load balancing traffic to all the pods and keeping health checks, etc. Now, the cool thing about this, and what makes this extremely useful for microservices, is that any service that you configure in your cluster is automatically visible for your entire cluster as a DNS entry. So as soon as you configure a service, this service is available for everyone. So if you're configuring multiple load balancers, multiple services, you can make them either software-driven or delegated to your cloud provider. And in any case, these are going to be visible as a DNS domain name everywhere in your cluster. So how does a service find the pods? We have seen how to create a pod. We have seen how to create a service. How do I connect these two? You connect services with pods using labels. And labels, as you can see here, labels is any combination of key values that you want to use. So you can say, I'm going to say type equals production, I'm going to say version equals 1.2, or tier equals front end. You can say whatever you want to your labels. Or you can say, for example, type equals WordPress. And when you're defining a service, you can say, OK, this service is balancing to any pod with this label. So any pod with the label type equals WordPress, I am the guy that is going to be balancing traffic to those. This is the way that you're connecting services with pods. Labels are not exclusive to pods. They're extremely useful in this concrete context, but they can be applied to services, nodes, pods, whatever. The whole idea of this is to be able to manage them as cattle instead of pets. How many of you are familiar with pets versus cattle? OK, so I'm going to tell this story anyway because like half of the audience. So the way we used to do things in the old days was that we were treating servers as pets. You define a concrete name for each server. You choose a common theme for the names of the server. So I'm going to go with Disney characters. This is Mickey, this is Minnie, this is Pluto. Pluto has a problem, so I'm going to connect to Pluto and find out what is wrong with it. So when your pet gets sick, you connect, and you take it to the veterinary and fix it. With cattle, this is not the case. First of all, cattle have terrible names, like Europe West 1B GCMH1220. And when cattle get sick, you don't take it to the veterinary. You kill it, you get another. What happens with these kinds of servers is that if one server is giving you problems, yes, you connect to the server, yes, you diagnose the problem, but you don't fix the server, because if you do that, you get a snowflake. You get a specific server with a different configuration, and you don't want that. You want all your servers to be equal, because remember, we're talking about managing a cluster, not individual nodes. So yes, you find the problem, but you fix it in the template that you're using to create your whole cluster. So all the tools that you're going to see in Kubernetes, they are designed to manage sets of whatever, and sets of pods in this case. Sets of pods are managed by applying a label to them, and then saying, this is the service for any pod with this particular label. So we have pods, we have nodes, and we have services. This is an example of service, how they look like. So kind equals service, type load balancer, which would be a Google Cloud Platform load balancer. The alternative would be a software-driven load balancer. And then selector with the label that you want to use to select. This is enough to manage traffic. Keep up your pods, direct traffic to your pods, and load balance this traffic. But how do you make your system resilient? If your pods fail, how do you reboot them? And this is where replica sets gets in. Replica sets are a way of specifying the number of replicas that you want for a specific pod. So the whole idea of this is that you have a set of pods, you define your pods, and then you say how many copies of this do you want. What you can see here is how a replica set is going to be taking care of 4 different pods. If a pod fails or if a node fails, the replica set is going to detect, I don't have enough pods running, I'm going to start more. Replica sets can also auto-scale. You can specify either I want 4 pods of this, or you can specify I want between 2 and 5 pods, depending on CPU usage, depending on whatever metric you want to use. For those familiar with Kubernetes 1.1, which used to be with the case of replication controller, replica sets is exactly the same concept, only more flexible in terms of labels. How many labels I'm allowed to use, how flexible these labels are. So you can specify a filter where you say, not just this is the value of my label, or my label is different from this, which is the case with replication controller. With replica sets, you can say anything that has this label, or that doesn't have this label, or that environment is one of production QA. Funny story, you can use labels, for example, for your zones. So you can say, OK, any node that is in Europe West 1B, or any pod related to this zone that is being deployed on this zone. Replica sets are not expected to be used directly. Replica sets are expected to be used inside of a deployment, which is the last entity that we're going to be talking about. So we have pods and nodes, we have services, and we have replica sets. And replica sets is an internal part of a deployment. A deployment is a way of declaring how you want to deploy your image. So you define, this is my image, this is the number of copies of my image that I want to have. The great thing about deployments, which is available since Kubernetes 1.2, like a couple of months ago, is that you can define your deployment, you can launch it, and then you can stop it at some point. So let's say that you say, I want 4 pods of this kind, and then at some point you stop it, and you say, stop it here. Now I used to have version 1. This deployment is about deploying version 2. I want this deployment to happen during the next 2 hours, and then at some point you pause your deployment, and you say, OK, stop it here. Take a couple of days. You are A/B testing. Now you have version 1 and version 2, both accepting traffic. And if everything is fine, then you can say continue. And if it's not, then you can say rollback. Kubernetes is not going to take all your pods down and then up with a new version. It's going to do it incrementally. So it's going to always have some pods accepting traffic, and it's going to confirm that the new pods are accepting traffic as well with whatever health check you have defined. So if your health check is an HTTP request to the root folder, that's the one that is going to be used to know if your pod has been correctly deployed. Last but not least, deployments keep a history. You can roll back as many deployments as you want, provided that you have your images in your container registry and they are still there, which they should. Then you can roll back as many versions as you want until you get to version 1. This is an example of how a deployment looks like in real life. So as everything, kind deployment, how many replicas do I want? And what follows, this template here, is your definition of a pod. Is how you define, OK, this is the pod. Pods are typically not deployed alone. If you deploy a pod alone, as is, like our first example, then if your pod fails, it's not going to be restarted. You need a replica controller for that. You need a replica set for that, meaning that you need a deployment for that. This deployment is about, I want 3 replicas. These are the labels that my replicas are going to have. This is the labels that I'm going to apply to my pods, that the service is going to do to configure the load balancing. And this is the image that they want to deploy. In this case, Nginx, the standard Nginx image from the standard Docker registry, and 1.179. You can use here whatever container you like. If you do that, and if you create that YAML file, and if you apply that file, like here, kubectl create this file, what you're going to see next time you ask for the number of deployments, you're going to see something like this: desired 3, current 0. Something that we learned with Borg is that the status of your cluster and your desired state of the cluster are 2 different things, and it's not a matter of seconds to switch from one to the other. So you may want 3 pods of this. Me being able to deploy that, that's a different story, because maybe I can, maybe I don't. Maybe I don't have enough nodes. Maybe my nodes are on fire. Maybe everything is wrong in the world, and I just cannot do this. So what Kubernetes is going to do is going to accept the desired state of the cluster, and then it's going to try, and it's going to be keep retrying, but you don't. It's not the same thing, your current state and your desired state. And this is something that you can see everywhere in the command line. Like here, desired status 3 pods, current status 0. And at some point, when you ask for that same command again, tell me the current status of my deployments, desired state 3, current state 3. One quick note about performance. When you're deploying pods in Kubernetes, pods take like 5 seconds to get started. Compare that with a standard virtual machine on Google Cloud. A standard virtual machine on Google Cloud is going to take between 30 to 45 seconds to get started. So this is like 9 times faster. OK, so I have a deployment, and I have been deploying 3 copies of my pod with version here, 1.7.9. This is perfect. And now I want to upgrade my application. I have a new version, and I want to deploy a new release of my same virtual machine image. So I go to this file, and these are YAML files that I can have on Git, which is great because I can recreate my entire cluster on premises, on Google Cloud. I can create a development environment. I can do it wherever I want. So I want to upgrade the image. I make the change to the file, and then I ask kubectl apply this new file. And what you're going to see here is the up-to-date column is different. Yes, I have 3 pods. I want 3. I have 3. But now up to date, with the new version number that you have provided, up to date I have 0. And at some point you're going to see up to date 3 if everything is going fine. If Kubernetes is detecting that the new version is not deploying correctly, it's going to pause it at some point. And you're going to see that the logs are awesome for that. You're going to see logs for everything. I couldn't deploy a pod. This is the exact reason why I couldn't deploy it. When deploying pods, it's considered best practice to specify the limits to the resources that you are going to be consuming. So you can specify that per container. You can say, this is the minimum number, and this is the maximum number of resources that your container is going to take. So request is the minimum, limit is the maximum. And we're talking about either memory or CPU. CPU is in units of 1 core. So here, this is 1/4 of a core of a virtual CPU in the case of Google Cloud Platform. And here, the MI is megabytes, which is a fancy word for megabytes. If you search that on Wikipedia, I had to. Megabytes are just megabytes. It's the same thing. So here we have 64 megabytes. Here we have 128, and CPU between 1/4 and half of a CPU. There is this. If you try to deploy a pod, and it's going to happen if you ever work with Kubernetes, at some point, you're going to see a pod that cannot be deployed. Like, deploy 3 of these, and then only 2 are being deployed, and 1 of them is not going to be because it doesn't have enough resources. If you don't specify limits, your cloud provider is going to be providing you with limits, which, if I recall correctly, in the case of Google Cloud, it's 1 CPU, if I recall correctly. So these are the limits that are going to be applied, and if a pod requests CPU 0, it can always be scheduled anywhere, in any node. So that's one way of guaranteeing that your pod can always be deployed. Now, about fairness of resources. Where is your pod going to be deployed? And this is the algorithm that Kubernetes is going to follow by default. So by default, Kubernetes is going to choose a node with a lot of space, with a lot of resources available. Kubernetes is going to try to keep your pods separate in different nodes. So if you're deploying 3 pods, Kubernetes is going to try that the 3 of them don't go to the same physical machine, so that if the physical machine dies, at least some of your pods are running somewhere else. CPU and memory, Kubernetes is going to try to keep them balanced. And you have, since Kubernetes 1.2, you have node affinity. You can mark where you want your pods to be deployed. And in Kubernetes 1.3, it's expected to have node anti-affinity. Like, I don't want my pods to be here. In general, the default scheduler works fine as it is, so you shouldn't have to spend too much time configuring this. Other components in Kubernetes that you can use to configure. Persistent volumes. Docker containers are expected to be stateless if possible. This is something that is good for cattle. I mean, if you have cattle and then you're adding a persistent state to this cattle, if you're adding a persistent volume to cattle, auto-scaling, for example, is much harder. It's still possible, but hard. And probably not possible in most of practical cases. The thing is that when you have a virtual machine, when you have a container, and you're adding state to the container, now suddenly you cannot auto-scale, for example, because what happens with your persistent storage? I mean, if I'm saying that I want it between 3 containers and 5 containers, and then I'm attaching a persistent volume to each one of these, if one of them is stopped, what happens with the persistent volume? You cannot just not have this persistent volume because it's necessary. It's either MongoDB or MySQL or something that needs this persistent volume to be online. So when you're deploying with state, typically you're going to be thinking about pets, which is fine. I mean, deploying with pets has a place to be. You can deploy persistent storage either outside of your cluster or inside your cluster. And if you're doing that inside your cluster with Kubernetes, you have options. You can either use pets and say, OK, this file, with this pod, this is 1, and this persistent volume with this pod is going to be a different pet. And then scale with that. That's perfectly fine. Or you can use claims. You can define, this is my set of persistent volumes, and this is my set of servers, and now let them connect however, in any possible way. So persistent volume is one way of connecting persistent state to containers. Then we have secrets, which is a way of communicating sensitive information to your containers without having to do that manually yourself. So secrets are going to be configured and injected into your cluster. They're going to be stored encrypted, and then you can use them from inside your containers. Namespaces to separate concerns, to separate an entire cluster from an entire set of components from a different set of components. Daemon sets, which are containers that are expected to be running in each node. And then jobs. Everything that we have been talking about today are about services that are always up and running. We talk about a WordPress or a MySQL server, and these are always up and running, and they are never going to be stopped. Jobs are expected to stop. They are expected to run, and at some point, give a success result. If your job is failing, then your job is going to be retried. If your job is never ending, then your job is going to be retried as well. Your jobs are expected to end at some point. What we don't have yet, and it's in the roadmap, are cron jobs, expected to run at a certain point in time. And this is something that is coming, but we don't have yet today. So the cron side of it, you would have to do that yourself. But for batch jobs, this is awesome. So Kubernetes, what we have seen here, is 100% open source. it's independent of the provider that you're using. So you can deploy that in your data center, in your laptop. You can deploy that on your cloud provider, be it Google or not. And one of the ways of deploying Kubernetes on Google Cloud would be Container Engine. And if you're going to just remember one thing about Container Engine, be it the first line here, is the easiest way to get started with Kubernetes. Because you barely have to do anything. I mean, configuring a Kubernetes cluster on Container Engine, it's one line of code here. Create a cluster, give it 3 nodes. This one here, I'm not specifying the size of the cluster, so it's going with the default. Create this cluster, give it 3 nodes, that's it. Second line, it's configure Kubernetes to talk to this cluster. So this cluster that I just created, configure Kubernetes to be talking to it. And then from here on, it's just Kubernetes. You can just start using it. And from here on, it means that you're using an open source tool that is independent from your cloud provider. So if you want to leave Google Cloud at some point, you can do that. It's only that this is the easiest way to get started with Kubernetes. And then if at some point you want to manage your own cluster, move to something else, take it to your own data center, you can do that. So Kubernetes is the result of 10 years of learning stories with Borg, of learning that expected state, desired state, and current state is not the same thing, learning that you need to manage a uniform set of resources to be able to deploy, that you need to be able to inject these names, these stable names that are associated to ephemeral entities. Kubelets, Borglets, we have much of the names that we have in Borg have been migrated as is to Kubernetes, and you're going to see that in the documentation as well. It's open source and available today. It's one of the most active open source projects on GitHub. And the whole idea is about managing your entire cluster, not managing individual nodes. So this is it. This is my time. Any questions? Yeah, on time. Eso, ahí va.
It's a very good one. I was amazed at the point where you said that the way you specify how you want to get to a specific state is just the guardian. But it sounds to me similar to these SQL execution plans that are so magical. And you end up letting you know how they work in order for them to be efficient and all that. Is there any such problem with your technology?
Sorry again? Is there?
There is such problem with your technology. I mean, is it so magical that you don't really need to care about how the system gets to the state that you declare? Or do you need to get to know a bit more about how it works internally in order for it to be really efficient on, for example, the time it gets to get to that specific state?
So in the older version, if I'm following correctly, in the older versions of Kubernetes, it used to be something that worked on the client side. I mean, upgrading to a new version used to be something that happened in your command line, not on the server side. What we have with deployments, and that used to be called a rolling update. What we have with deployments is something that lives on the server side, on the master. And this is precisely to remove all these gotchas of I close my command line and suddenly my rolling update, I don't know where it is, or I want to roll back several times and I just can roll back once. This rolling update that is running right now. So the whole idea of this is the second iteration of something that was available from Kubernetes 1.0, if I recall correctly. And with Kubernetes 1.2, the whole idea of this is move it to the server side, move it to the master, and make it more stable. Like less surprises, like you say. As far as I know, I haven't heard about many of these, many issues with that. The only issue that happens is that if you have a server and you're using hashed resources, like adding a hash to any JavaScript file, and you're doing a rolling update in this way, like 2 different deployments, if the hash changes, one request can go to the wrong server. And then you're asking for this JavaScript file, and it's going to a server that is serving version 1.0 instead of version 2.0. And there are solutions for this, but that one gets a little bit trickier. Yeah. More questions? OK. So can you pass it? Yeah, careful. OK. Almost. There you go.
Thank you very much for the talk. My question is quite simple. Do you know what version of Kubernetes is currently running on Google Container Engine?
So the difference in, just to get a visualization of this, the team that is deploying, the team that is developing Kubernetes sits here, and the team that is developing Google Container Engine is like here. So what you can expect is more or less 1 week between the release and it being available on Container Engine. Now, your master is going to be automatically updated at some point during that week. Your nodes are going to be updated by you. So you have a command line to do that update. But it's not going to update Kubernetes on your behalf unless you want it to, because it doesn't, the whole idea is not breaking your cluster. So the master is going to be automatically upgraded because this is something that Google controls, but your nodes are not under Google direct control. I mean, you could be making changes to your nodes. And just for that, your upgrades are going to be done by you. You have a command line for that. But typically, 1 week between a version of Kubernetes is released and it's available on Container Engine.
Okay, and what version is actually in production?
Sorry?
What version is currently running in production?
What we have right now in production is 1.2. 1.3 is coming now in summer. I mean, the rhythm of Kubernetes is crazy because it's like 3 months between versions, between minor versions. I mean, 1.1 was just before Christmas, if I recall correctly. 1.2 was a couple of months ago. And 1.3 should be now in June, approximately.
Thank you very much.
Thanks. Back there. I love that microphone, by the way.
So thanks for your talk. And I have some questions. First one is there support for other cloud container native support?
Sorry, can you?
Is there support for other cloud native container support like AWS, ECS?
If you go to kubernetes.io, you're going to see there an Ansible playbook for any cloud provider. So if you want to deploy on Amazon Web Services, you're going to find there step-by-step instructions about how to deploy on Amazon. And they're going to be developed by Amazon engineers and Azure engineers. So you're going to see there, also you have DigitalOcean, Linode, I think Linode as well. You have any cloud provider is available there, and also your own data center.
Okay, but deploying AWS, you mean deploying instance, a VM in AWS that runs containers, or run container natively in AWS in ECS?
Sorry, didn't get that.
When you say running AWS,
Yeah.
you mean running a VM in AWS that run the container, or run the container natively?
No, I mean that you're always going to be running on EC2 on AWS. Same way as if you're deploying on Google Cloud Platform, you're really running on Google Compute Engine, which is the equivalent to EC2. Yeah.
Is there an UI for Kubernetes?
Any?
An UI? User interface?
Any?
UI. Like
UI. Oh, so I can tell about what you have on Container Engine, and Container Engine is only going to provide you with a UI, with a web UI, to manage your cluster, not internally Kubernetes. Since version 1.2, you have a better UI because Kubernetes is giving you a basic UI, and you're going to see that, like basic UI, some very similar, very limited ways of knowing what is going on inside of your cluster. Then on Kubernetes, you can connect your own monitoring and logging tools, meaning that, for example, on Google Cloud, it's cloud logging and cloud monitoring. But you can use anything else if you like. And that means that if you want to see the CPU status of your pods or memory status of your pods, you can do that. Outside of Kubernetes, outside of Container Engine, you have cloud monitoring for that. And you can use any other tools in that same way. Regarding UI, Kubernetes is giving very limited UI and mostly for monitoring, but what you have is other set of tools that are built on top of Kubernetes. So for example, you have Red Hat OpenShift, which is an entire UI, an entire web interface to manage Kubernetes clusters. And being Kubernetes, it's independent of which environment you're running it in. My understanding is that CoreOS has the same thing. But I don't remember exactly the name for that one.
my last question is there a way to have like pipelining deployment in Kubernetes? I mean, deploying one environment and then from
You have namespaces, so you could be creating the same cluster with different namespaces inside of the same infrastructure. That's one option. So you can configure your cluster and then say, OK, deploy with this namespace production, deploy with this namespace development, which is risky, and probably I wouldn't recommend that. You can just use separate clusters, and again, since these files, these YAML files, are just files that you can save on Git, so you can just create a cluster here, now create a separate cluster for this there. This one has 10 nodes, this one has 1 node, and start deploying.
The question is, who orchestrates deployment?
Who orchestrates? So when you are configuring a Kubernetes cluster, the configuration of the cluster is not that simple. And in the end, it's a master and a set of nodes. The orchestration is done by the master, which is always a separate thing. When you're configuring your cluster yourself, you have to configure that master, give it a name and last name, etc. When you're using Container Engine, the master is transparently created for you and configured for you, but still there is a master. The whole orchestration thing, your command line is communicating to the master, and the master is then taking care of it. Okay. Welcome. Any more questions? OK, then. Thank you very much.